We'll continue kind of where we left off. We were in the process of talking about some of the analysis challenges in designing steel lateral load resisting systems. And we've gotten to the topic of when you're doing a computer model of a frame, what are the options available to the designer on modeling the joints or dealing with the joints, let's say in a moment frame. Well, one of the nice things about all the horsepower that you have in your desktop now with these programs, a lot of them have the ability to actually put a spring at each node and allow you to use that in the attempt to model the stiffness of the joints. And clearly, like this slide here shows, you can do that. You can, some programs like ETABS, for instance, you can take part of the joint as rigid, 100% rigid, 50% rigid, 75% rigid, or whatever. What we found when you're modeling moment frames for wind, that it's probably, unless you're going to go to the trouble to specifically model the joint with panel zone deformation stiffnesses included, which most practicing engineers don't like to do in their routine everyday design, the next best thing is probably to not assume that there's any rigid joint area, but actually to model the frame from center to center of joint. And by doing that, and studies have shown this, that you are accounting a little bit for some of the panel zone deformation that you get. So I think the bottom line is would not recommend that you take a beam column joint as an infinitely rigid element and then model the clear span properties of the member and then take the joint as rigid. That would not be a wise thing to do, because you'll certainly underestimate the deformations caused by panel zone. And studies have shown that if you actually do go to the trouble to accurately model the panel zone deformations, you find that there are significant, or can be a significant, proportion of the total drift that you get from flexural deformation of columns and beams and shear deformation of columns and beams. And then, of course, you've got the axial deformations from columns. So I think our recommendation is, unless you're going to go to the trouble to do a more accurate model, we would suggest that you model center to center of joint for steel moment frames. But as I say, many computer programs have ways to account for the panel zone deformation if you want to go to the trouble to accurately model it. For 30-foot to 40-foot spans is probably reasonably accurate. Just take the center to center distance. If you're doing a tube building like we do in high-rise, where you got your columns at 10 foot on center around the perimeter or 15 foot on center, there you want to perhaps take a serious reevaluation of how you're going to treat those joints and actually make an attempt to model the panel zone deformation component. And of course, when you design a concrete frame, you have these same issues that you have to deal with. How much of the joint do you take as rigid and how much do you take as flexible? But we won't get into that here. This slide also just shows that you can, in a lot of this modern software, input the properties that would allow you to model the panel zone deformation if you so desire. This next series of slides, we're going to talk about design of brace beams. And when I say brace beam, as I mentioned earlier, I'm talking about beams that are part of braced frame systems, like the beam involved in a chevron bracing system or the beam involved in an X-brace or a diagonal brace system. Those elements are unique in the sense that not only do they potentially have gravity load on them, but they also could have large axial loads on them. And so you end up having to design those elements as beam columns. And how you model those is important, and more importantly, how you take their unbraced lengths of those members is also very important, because I think a lot of engineers make some errors there that I want to point out to you in these next series of slides. Also, if you use a program like ETABS or any of them that have the diaphragm, rigid diaphragm capability, you have to be very careful that the rigid diaphragm assumption is inhibiting the axial deformation of this brace beam. Because if you connect it to the diaphragm, the rigid diaphragm, and there's no deformation in a rigid diaphragm, and therefore there would be no deformation in your brace beam, and you would be underestimating some of the drift caused by the shortening of this brace beam. So that's another consideration that you have to be careful of when you're modeling an X-braced or a chevron brace system. And as I mentioned, this unbraced length, what I'm calling KL major, KL minor, and then KLZ, that is, you not only can have flexural buckling about the x-axis and flexural buckling about the y-axis, you can also have torsional, flexural torsional buckling. And most, if not all, post-processors that design these elements as part of the software do not, to my knowledge, consider torsional buckling. Yet torsional buckling, as you will see here in a minute, could control the design of these members, and you have to be very careful of that, and we're going to get into that here in a second. So this particular example that we show here is a diagonal brace, diagonal concentric brace system. Let's say it's part of an office building that has a floor system, concrete composite slab. And because of that, the KL minor, we call it here, would be 0 because the floor system is bracing the top flange of that element. The unbraced length about the major axis, with the web and the plane of the slide there, clearly makes KL major 30 feet, or the 30-foot span element in this case. Now the question is then, if you, what is KLZ in this element? Well, it's probably close to 30 feet because it's not really being restrained from twisting. So one of the things you'd want to consider doing here is if you take KL minor as being 0 and design for KL major as a 30-foot unbraced length, you are potentially ignoring the limit state of torsional buckling for that member. So one of the ways to trick the software is to, instead of putting KL minor as 0, it's conservative and reasonably accurate to say that KL minor is 30. Then your post-processor, if it's designing the element, would design it as an unbraced length for flexural buckling about the weak axis of 30 feet, thereby indirectly accounting for the torsional buckling possibility that exists here. So be careful of that. I think there's a lot of people that would design that brace beam for KL major of 30 feet, KL minor of 0, and forget about torsional buckling as a potential limit state. And the same is true if you say, okay, I want to put a kicker there at mid-span, assuming you don't have an elevator shaft or something in the way, and you can make KLZ 15 feet because you can say that kicker braces that brace beam against torsional buckling. But then again, KL minor is still 0. So again, if you're going to account for the torsional buckling limit state, which may or may not control, compared to the KL major unbraced length distance of 30 feet, you would probably want to trick the software into saying, okay, let me design for KL minor of 15 feet, and thereby I'm indirectly accounting for the limit state of torsional buckling. So that's the point we're trying to make here. You've got to be careful when you design these brace beams and what assumptions your post-processors might be making, or what assumption you're making if you design it by hand. In the case of this chevron brace, in this case KL major is 15 feet, right, because it's the brace itself is bracing it, the beam. KL minor again is 30 feet, or 0, assuming we have a slab. And then torsional unbraced length is still 15 feet, assuming we're going to put a kicker there at mid-span that would control the torsional buckling. So again, you have to be very careful about what your real unbraced lengths are for those three different limit states: flexural buckling X, flexural buckling Y, and torsional buckling Z. If you have an elevator shaft, a chevron braced in an elevator shaft, I've seen some engineers assume that the elevator divider beam is going to provide bracing. And physically that might be reasonable, but from a code standpoint, the elevator divider beam is not fireproofed, and therefore one could argue that it probably shouldn't be counted upon as being a bracing element. So you need to factor that into your design thinking there as to how you're going to design that brace beam for that case. And the same applies here for the diagonal brace. So be careful about the openings and the unbraced lengths that you're assuming. Now, I mentioned the issue about foundation modeling and the fact that having a realistic boundary condition at the foundation might help you in designing for drift, where drift can control moment frames. It's been standard practice for many years in the AISC specification to say that if, rather than assuming a pin base, that most footings or foundation systems would really permit a rotational stiffness more akin to assuming G equal to 10, where G is the ratio of I over L of the column and the summation of I over L of the girders that frame into that joint. Taking a G equal to 10 is a reasonable boundary condition. I think this is based on a paper by Ted Galambos many years ago that derived this, and it's been part of the nomograph discussion in the AISC specification now for many years. But so what we do is when we're designing moment frames for foundations, we frequently take G equal to 10 and assume a rotational spring at the base that provides that level of rigidity, and then take advantage of that in reducing the drift under a serviceability limit state, which I think is pretty reasonable to do. If you want to take the foundation as rigid, then of course you have to be consistent in your assumptions. If you're going to assume the foundation is rigid when you're designing the moment frame, then you have to translate the moments that you get from that analysis into the foundation design. And rather than assuming it's perfectly rigid, you might want to assume that it's more a G equal to 1, which is another boundary condition that's identified in the AISC specification as being more realistic for the so-called rigid foundation condition. The point is to take more realistic boundary conditions into your analysis into account as a vehicle to reduce drift, which controls moment frames most of the time. So different programs allow you to handle this different ways. Some of them allow you to just put a spring down there at the foundation, and using G equal to 10 you can solve for the spring stiffness that we show there, case of C, that makes that condition happen. Or if your program doesn't allow a spring, you can put a pseudo girder down there that has the properties of that girder giving you the rotational stiffness that's comparable to G equal to 10. So there are different ways to handle that in your modeling. If you look in the PCI handbook, they have a modeling suggestion for accounting not only for the footing stiffness of a spread footing, for instance, that with a soil that has a certain modulus of subgrade reaction, but it also gives you some ideas on how you might model the base plate and the anchor bolt assembly, which could be an additional source of rotation at the base. We usually don't go to that kind of trouble, and we just assume that G equal 10 and go about our business for the average frame. But if you want to get into this in more detail, of course, we now have the tools to do these more sophisticated models fairly quickly. Okay, we talked about the various analysis 1, 2, and 3, serviceability, strength, and stability. Now what we want to talk to is, well, what are the acceptance criteria? We mentioned that under serviceability, that not being a code issue, not code specified, the engineer is free to use his judgment. And what we do in our practice is use a drift limit of 0.0025 or 1/400. And then depending on the kind of building, we either use the 10-year wind or the 50-year nominal wind to check that drift limit against. And then we do everything we can to accurately model the frame. That is, we consider the composite stiffness where it exists. We consider the foundation boundary conditions to do as good a job as we can in predicting the drift under the service load combination that you're assuming. That includes, in my opinion, this is one man's opinion, that you need to consider the P delta effect in the drift calculation. I know there's some engineers that say, well, wait a minute now, these drift ratios all came about 100 years ago in Chicago and New York, you know, when they designed for 20 pounds a square foot above 100 feet, and that's when 1/400 was born. And so that was all based on a first order analysis, so I'm going to do mine based on a first order analysis. Well, that might be okay if you're a traditionalist, I guess. But if we're ever gonna move forward in trying to more accurately predict deformations in our frames, we got to do a better job of modeling them. And we know that second order effects exist. The P delta concept is very well researched and documented, so we know it's there. So if we're really going to get meaningful drift checks, we need to do a meaningful model as best as we can, and we need to capture the properties of the frame as best we can. And then the other part of it, perhaps the more difficult part, is we got to get drift limits that are realistic with the materials that we're using. And therein perhaps where more research is needed. What is 1/400 acceptable for masonry and drywall partitions and glass? And maybe that there's a whole family of drift ratios that should be applied depending on what your cladding and partition types are. It turns out, if you do some research on this, there is some data out there that says, okay, if you rack a story this much with a drywall partition, it takes this much drift to cause the first cracking of that partition. And there's some data out there that suggests the same thing for masonry, clay tile masonry. And so there is some data that exists, but basically what's missing, of course, is all the myriad of cladding systems that exist today and what their drift limits are that cause damage. But for want of other information, I would suggest that 1/400 is a fairly reasonable number. It's worked, and therefore that might be a good limit to use. For analysis 2, the strength limit state, again, the code tells us what to do here. And the P delta effect, we try to control that in our design practice to a Q value of 0.25, which translates to a P delta effect of 1.33. Now, some engineers say that's too low, and some people push it all the way up to 1.5 or even 2. I don't like to see second order effects in my frames get much higher than 33%. Because I think you're starting to get a kind of a soft building when you go much higher than that. But you're free to pick that number. All the code tells you is you have to design for whatever P delta effect you have. So in-house, we use the P delta limit of 1.33. That is, we put enough stiffness into our frame to prevent that P delta effect from being any larger than 1.33. Under analysis 3, the stability, the 99 LRFD spec actually had some requirements in there for stiffness of brace frames. It was sort of hidden in there that a lot of people didn't realize it was there. We've rewritten all that in the 2005 spec where it's sort of taken out, although the whole new direct analysis approach has been born. I don't know if any of you have seen the new Chapter C in Appendix 7. We now have a whole new way to do lateral analysis for steel frames using a direct analysis approach, which basically is downgrading the EI of your members to 80% of the gross value. It's sort of taken an approach not unlike what they do in concrete, where you downgrade the EI stiffness from gross to some number that accounts for all the cracking. Well, we're doing the same thing in steel now with this direct analysis method. And the 0.8 is accounting for the fact that the frame softens as you approach the ultimate limit state. You get this spread of plasticity at the joints, which softens the frame and reduces the effective stiffness. The 0.8 factor now accounts for that. And then the new direct analysis method also is basically based on the notional load concept, which you're going to be hearing a lot about in the next couple of years as seminars start being developed for Appendix 7 and Chapter C in the 2005 specs. So I'm not going to go into that anymore, but what I did want to say here is that the concrete code does have a limit on this Q value, and it actually requires you to check under sustained gravity loads. It limits the Q value. And we've got our own practice. Steel doesn't have that same explicit limitation now in the 2005 spec, but we have our own. We say under the factored gravity loads that we're going to limit that Q value to 0.375, which means we're limiting the P delta effect to 1.6. And so that's our rule. When will that control? I think we got a slide here in a minute that will tell you about that. Before I get there, I just was going to tell you about, I wrote a paper way back in 1993 that studied this drift issue. It was an engineering journal article. And it talked about just lateral racking or lateral drift of a story really isn't necessarily the right parameter that we should be studying. The right parameter is whatever it takes. If you take a typical floor and you look at a rectangular panel, from the floor above to the floor below, from the column to the right to the column to the left, what you're really trying to do is say, okay, what shear strain is that rectangular or square panel subjected to? It's the shear strain that causes the damage. And it turns out that in high-rise buildings, that shear strain is not only a function of the displacement of one story relative to the story below, it's also a function of the column shortening of that column on the right compared to the column on the left. That's differential column shortening is also a component that causes shearing strain and therefore damage. And so in this paper I proposed a different definition of drift. It's not just one story displacing relative to another, but it actually looks at, for any rectangular panel from one floor to the next, it looks at the shear strain, and all you got to do is get the displacements at the four corners of that rectangle from your computer model, and then plug into this equation, which I call the drift damage index. And this is actually a better measure of shear strain undergone by that rectangle than just the racking of it. So if you visualize the column, if the column shortens, that also induces a racking. So it just factors that component into it. For low-rise buildings, it doesn't matter because you're not getting any appreciable column shortening. It only makes a difference for tall buildings. And so that's why this new definition, I think, is appropriate. So we talked about the story stability index, Q, as being P delta over VH. It's important to understand that just because you have a drift limit and you design for a certain drift limit under wind load, that doesn't necessarily guarantee that you don't have a story stability problem. Why is that? Well, buildings that have potential story stability problems include buildings that have very low lateral load requirements, and those might be buildings in a very low wind zone, like an 85-mile-an-hour wind zone, like they have on the West Coast or down in parts of Mexico. Buildings that can currently have real heavy dead loads, like clay tile partitions and big thick floors and heavy cladding materials. And this first came to my attention when we were designing a building down in Mexico, in the central part of Mexico toward the West Coast. They had no seismic to speak of, and very low wind loads and very heavy building materials that they use down there. And we found out that on that kind of a building with no lateral loads, that means it doesn't have much lateral stiffness because you're not putting much lateral load on the building. Therefore, it's a pretty soft building, stiffness-wise, in the lateral direction. At the same time, you have a large P, a lot of gravity load. Well, a large P and a low lateral stiffness produces a potential story stability problem if you look at what controls story stiffness. And it's basically the gravity load on the story and the stiffness of the story. Now, to take an example here, look at this rectangular building, and I'm going to tell you a famous building that had this very problem. This building has obviously a big wind sail in the B direction or the Y direction, right? And yet it's very narrow in the X direction because the wind sail area A compared to wind sail B, A is much smaller. So if you design this building for a certain drift index, you actually may have quite a bit of stiffness in the Y direction because you got a lot of wind area that you're designing for. But in the X direction, you don't have much wind area. It's much narrower face, yet you have the same weight, the same mass that you're carrying. So now when we look at what Q is, remember Q is that stability index, it's P, the weight on the story, divided by the stiffness of that story, and then the story height's H. Well, you find out that because there's no wind sail in that X direction, and yet you still have the same P, you actually can have a stability problem in the X direction of this building, much more likely than you would in the Y direction, because the stiffness in the X direction is much smaller. Why? Because you designed it for drift, and there's no wind load that you're designing for, a very small wind load. Now, interestingly enough, there's a very famous building that looks a lot like this in plan that had this very problem. And the Boston Hancock building. Anybody remember that building? John Hancock building in Boston. Very long, narrow building. And that poor building was designed by I.M. Pei, won all kinds of AIA awards, beautiful building. But that building was snake bit when it comes to its structural performance. And it had a myriad of problems. First of all, it had a major glass problem, which we all probably heard about and won't discuss here, but all the glass ended up being replaced. That was one problem. It had a foundation problem that ended up getting fixed. But what most people don't know, it also had a very serious stability problem in the long direction of the building. It had moment frames in the long direction that were designed for drift, and it was such a soft building that it had a serious, very serious P delta effect, to the point that when they ended up fixing the glass and fixing the foundation, they came back and stiffened the frame, and at the same time they put a tuned mass damper on top of the building that Bill LeMessurier designed to control perception to motion in the top floor of that building, because it was so soft it was very sensitive to acceleration under the high wind loads that you can get in Boston sometimes. So there are real world examples where this stability can get you into trouble. It certainly did on that building. Okay, that concludes the section on lateral load analysis, primarily for wind loads. We're going to jump into metal deck design and just some of the things about that. But before we do, I'll be glad to open it up to any questions anybody has on any of the material we covered under the lateral load section. Everybody had their lunch and they're ready for their afternoon siesta. Okay, we're going to cover metal deck design. This isn't rocket science, so you're not going to get anything earth-shattering here, but it's basically something that you don't pick up in school, and engineers that get handed a metal deck catalog on their project and say, go design this project. Gee, what is all this about? I never saw this in school. So we're going to just cover some very simple basics on metal deck types that are used out in the real world and the catalogs that come out with them and how you might want to interpret them. We're going to talk about the different deck types. We're going to talk about composite deck design, composite deck finishes and details, is what kind of coatings, painting, galvanization you want to put on these. Non-composite deck types like form deck and roof decks and other non-composite deck design issues. First of all, we already talked about composite deck. We know what that's all about. Got embossments on it where the metal deck is the reinforcement, positive reinforcement for the slab in non-vibratory conditions. The metal deck is the positive reinforcement, and you just put mesh in there to control shrinkage and temperature effects. There are also non-composite decks that basically can be broken down into form decks that are used for concrete support, where the deck is strictly a form to support the wet weight of the concrete, is not intended to be any reinforcement for the slab. So you put either welded wire reinforcing in there or reinforcing bars in there to reinforce the slab for gravity loads. And then there's all kinds of decks that are available for roofing support, roofing materials. Composite deck, I think we covered pretty well. Most of this is a repeat of what we already talked about. Just remember that under dynamic loading like forklifts or heavy vibratory equipment, you probably don't want to count on that composite deck as the positive moment reinforcing. You would want to reinforce it just like you would a normal concrete slab for flexural resistance.